Yeah, first of all, I want to thank you and Euclides and Nima for inviting me here. It's the first time in Brazil at the Unicamp, and it's a real pleasure for me to be here. Yeah. Here you have this picture. Yeah, I've seen it for many times at different institutes, and to explain where I am coming from, you have to look here on computational engineering. Say better, engineering. Computation, yes, we use it, yeah, but I was trained as an engineer, yeah, and grew up with plates and shells and bars and vibrations and so on. But later on, I went into the field of fraction mechanics, yeah, and fraction mechanics, yeah, in microscopic point of view is interesting for engineers, of course, but later I became more and more interested in the micromechanic aspect of fraction mechanics, and so I went more and more in micromechanics, and this brought me then in contact with people from material science, yeah, and they approached me. They have mechanical problems, and so we tried to help them with our methods. So more and more I came into in contact with these people of materials mechanics, yeah, and so for me, most of the problems now come from this field, yeah. Yeah. Sometimes I work also with people from geomechanics or geophysics, yeah, but this is more or less an exception. Now, today my talk is on modeling and simulation of electroactive materials and structures, and I want to present some results of our group, yeah, what we did during the last years, and yeah, and there is a point I know. I tried, yeah. Here, at least 3 names I want to mention. This is by Jiangxu, Ralf Müller, and David Schrade. All 3 of them were PhD students in my group. By Jiangxu now is a professor in material science at my university. Ralf Müller is a professor at the Institute of Technology in Kaiserslautern, and David Schrade is with him, yeah, now. There are a number of all other colleagues who contributed to several parts of this talk, but the list of names is too long, and this makes no sense to mention it. If the time really let me talk about these 4 fields, I will mention ferroelectrics, dielectric, elastomers, ferroelectrets, and nanomagnets. Nanomagnets do not fall in this electroactive materials, of course. They are magnetic active materials, but I have put it into this under this title. Okay, ferroelectrics, yeah, they are used in many devices. One very well known device is the fuel injection, what you have in every car nowadays, and Bosch, for instance, a German company, did a lot to developed these fuel injection systems, and the essential material what is used in this structure is a ferroelectrics. Yeah, ferroelectrics, they are used for actuators, sensors, and so on. And here it's an actuator. Yeah, dielectric elastomers. They are very soft materials. Let's see. No. Yeah. Very soft materials also work as actuators and sensors, and they are a good example for an artificial muscle. Yeah, and for this artificial muscle, it's really used. Ferroelectrets are very soft piezoelectric materials. Yeah, and one application is the acoustic in acoustic systems, in a microphone or in a loudspeaker, and such materials are used, and they are very soft materials. Yeah, and I will talk about this. And nanomagnets are materials where people have the hope that they can be used in computers, say, later on, and solve or help to solve the problem of packing. Yeah, the storage problem. Yeah. Okay. Let's start with ferroelectrics. Ferroelectrics, one typical ferroelectric is barium titanate, or PCT, and it has above the Curie temperature cubic structure, and the colored dots here, this is barium in blue, titan in red, and oxygen in green, yeah, and you see it's a nice centered cubic structure here. If the temperature is below the Curie temperature, you see that this system is no longer stable. It becomes tetragonal, and mainly the center atom is not longer in the center. It's shifted. Yeah, and there are, of course, 6 possible directions where it can be shifted. Yeah, on account of the say cubic structure above the Curie temperature. Here only one is shown here, and this gives rise to a polarization of the material, yeah, of this tetragonal structure. And this also gives rise then to the electromechanical coupling, yeah, of the material. Yeah. And now let's see. When we apply an electric field to such a structure, well, what happens? And if the electric field is relatively low, below the coercive electric field, nothing special is happening. Let's see what happens if we apply the field in the direction of polarization. This leads to an elongation of the tetragonal structure. You have a displacement or a strain of this structure. If you apply it in the opposite direction to the polarization, it will be compressed. But if the field is above the coercive electric field, then you get a switch in the position of this say green oxygen atom here, and you see it switch. For instance, here, when the field is directed to the polarization, the initial polarization, then the atom switches and gives rise to a new direction of the polarization. That's clear, yeah? And this then gives rise to the remanent polarization, remanent strains, yeah? And the switching can be done due to an electric field, but it also can be done by mechanical compressing or stretching of the system. Okay, this was, say, the atomic aspect. Now, let's see the microstructural aspects here. If you look with a microscope into this material, you see on the crystal level the domains. This means the crystal itself is structured, and the domains are separated by domain walls, and one domain is characterized by, say, one unique polarization. And the domain wall separates, say, fields of different polarization. Yeah? Then here on, say, mesoscopic scale, you see damaged domains here, on account of a crack. Yeah, and if you look at the real material as it is used in devices like this fuel injection system, then it's a polycrystal. Yeah. And it's a hard, stiff polycrystal like a ceramics, yeah? And within each grain, you find this structure here of domains, yeah? And the grains are separated by, of course, grain, I don't find the English word now. Okay. And if you look for the microscopic behavior, it's characterized by dielectric hysteresis and butterfly hysteresis. Yeah, here it's plotted the electric field or polarization versus electric field. Here, the mechanical strain versus the electric field, and these are typical, the typical curves you find in the hysteresis of the material. Yeah, but there are, of course, problems. Otherwise, people from material science would not approach people from mechanics. For instance, one is the electric fatigue problem, namely that you observe that the hysteresis loops become more and more, say, weaker in some sense. Yeah, so there you have a fatigue problem here, and it is not fully clear what the source of the fatigue problem is. Yeah, and people think the main reason is the agglomeration of oxygen vacancies. Yeah, and that they agglomerate and then block the domain walls that they cannot move. Yeah, and if they cannot move, you cannot have a switch in the polarization. Yeah. This can be one reason, yeah. Okay, as I mentioned just, but then there are other problems because it's a very stiff or brittle material. You have a problem with cracks, yeah. And so, because I came from fracture mechanics, I thought, cracking is one problem which might be interesting also for you here. Here you see from an experiment done in Darmstadt, a domain wall between, say, two domains with different polarization in a specific material, yeah, where the single crystal you had was really visible, yeah, with free eye, yeah, and where you very easy could see what happens, yeah. Now, there are, of course, different methods to attack such a problem. In this case, we used the phase field model, and to explain it, it's very simple. Yeah, you start with the balance laws. Yeah, you have to take into account, of course, the coupling between the electrical and mechanical problem here, the mechanical equilibrium equation, the electrical equation, then the constitutive relation, and here you see the coupling. Yeah, here this part is the pure mechanical part. Yeah, and here the coupling between this B, the piezoelectric tensor, what also appears here is a dielectric tensor. So you have to know all these, say, material parameters, and this is one big problem. Yeah, you can model, yeah, a lot of things, yeah, and you can do simulation and produce nice pictures, colored pictures, but these say material constants often are the source of the problem. If you are you compare experiments with the results of your simulation, yeah, and I will come later to this problem again. Okay, the kinematics and the relation between the electric potential phi and the electric field is here. These equations you can find in all, say, relevant textbooks, yeah. And then, yeah, with some thermodynamics, and you finally get to equation, say, Ginzburg-Landau type equation, where this H is an extended electric enthalpy, yeah, and the electric enthalpy it consists of essentially of three parts: the local classical electric enthalpy. I will show it later on the next slide. The domain separation energy and the interface energy. Yeah. So you have to take into account that, say, a domain wall carries some energy, yeah, and so for separation and for taking into account the domain wall, you need energy terms, yeah, and P here is the polarization. This equation, yeah, is an evolution equation for the polarization, yeah. Okay. Now the electric enthalpy, yeah, it consists of several parts. The first part is the pure mechanical part here, yeah, and then the pure electrical part here, and then the coupling, and then one term for the polarization, yeah, and epsilon naught here. Yeah, this is given by the initial polarization here, P polarization, as I mentioned, yeah, and here this tensor, yeah, PKIJ, yeah, it depends on the polarization. This means that the material constants, yeah, depend on the polarization itself, yeah. For simplicity, A was taken more or less as a unit tensor multiplied by a constant. This is the stability here. Yeah, and C also was, for simplicity in this simulation, was taken as a constant, but in reality it's not a constant. Yeah. Then the interfacial energy is given by this equation here, where some parameters appear, and I have not the time to explain each parameter, but essentially they describe the thickness of the domain wall. It's a field theory, yeah, and you don't say it takes not account into account, say, a sharp domain wall. You can do this, but then you don't work with phase field theory. Phase field method is a field, say, a field theory where all fields are in some sense smooth, yeah, and so the gradient of P, yeah, this is the steep, yeah, or say replace this jump over the domain wall, yeah. So these parameters epsilon and so on, they characterize the width of the domain wall, yeah. Yeah. And then for the separation energy, yeah, this is usual in phase field modeling. You take such a yeah. A function, yeah, say here p squared, then fourth, and so on. Yeah, you can take, of course, into account higher orders, but then you have a problem with all these constants which appear here. Yeah, and you have to identify them. Yeah. And here it's written down only for the plane problem. If you have a 3D problem, then P3 also appears, the third component in the third direction. Yeah. What you can model with this in 2D simulations are 90 degrees and 180 degree domains. Yeah. Okay, and here is this function, separation energy in some sort plotted, yeah, and where the minimas are, these are equilibrium positions, and they characterize certain polarization here, yeah. As they are given here, and the little arrows here, they are, say, the direction of the polarization. And here, this is a domain wall, a 90-degree domain, 180-degree domain wall. Here you see a 90-degree domain wall, yeah. And again, here, a 90-degree domain wall. Okay. And what we also very often use are configurational forces. This is nothing really new in say, new equations. Yeah, you can derive configurational forces from, say, the basic equations you use. Yeah, but configuration forces are a very nice tool. Yeah, because they describe the driving forces on point effects, on say, interfaces, and very convenient to use in material science, yeah, and the problems which occur there, yeah, and you can derive this in different ways, but what you get is essentially such an equation which looks like an equilibrium condition as you know it from mechanics, yeah. But here appears the so-called Eshelby stress tensor, yeah. You should not mix Eshelby stress with Cauchy stress or something like this, yeah. This is not, say, the pure mechanical stress. Originally, only this part appeared when Escher B for the first time derived this tensor. What you see here, H, we have explained it before. This is the extended electric enthalpy, and say if you work in pure mechanics, then it's nothing else than the strain energy. And here the gradient of the displacement and Cauchy stress here appears, and these extra terms, they come from the electric field and the coupling with the electric field. And this little g here, you can interpret it as a say as a configurational volume force. And what appears here, this is the mechanical volume force here. U is the displacement, phi is the electric potential. Q, these might be electrical particles, say electrical loading, say the volume distribution of electric loading. And what also appears here is the mobility. The mobility here, I should have explained it before. This is here this factor. Okay. What are reasons for that configuration forces appear? All inhomogeneities, singularities, point effects, distributed inhomogeneities, interfaces where the mechanical or electrical parameters change and the behavior changes. All these then causes configuration forces. And they are perhaps, if it's point effect, you have a single force acting on a point effect. If you have an interface, it's a distributed force distribution, and you can then, of course, compute a resultant configurational force. And these are driving forces acting on, say, all these inhomogeneities. And for instance, a driving force acting on a domain wall is given here. And the rules which you now can use, you can copy it directly from, say, continuum mechanics. Because this is a stress tensor, a specific stress tensor, and times n, it's a traction vector, and so on. So this is very simple. It's a really nice tool. Oh. What happens? Okay. Okay, then you have to introduce material parameters. And here you see a set of materials parameters we got from the people from material science. Okay, we put this into our code, and our code was, in this case, finite element method. You have here 3 nodal degrees of freedom, but behind this 3, number 3, of course, there's more. U is a vector, with 2 or 3 components, depending whether you work in 2D or 3D. P is also a vector, and so on. This is a scalar function. So, and you have to solve this evolutionary equation. We took implicit time integration. It's a nonlinear system, of course. Yeah, and but this is, say, standard in some sense. Yeah, how to do this. What perhaps is interesting here is that you more or less directly can compute these configuration forces in one step. Yeah, it's not a procedure, say, in addition after, say, the usual FAM computation. Computation, you directly get them. Yeah. Okay, here is one example. Yeah, say the evolution of a crack. Yeah, in a loaded system where the crack then propagates, and here are the formed domain walls here, and this, of course, is some sort of mess. You have to look a little bit closer, and then you see what happens in this at the crack tip region. Yeah, this is only an example. Now let's consider some cracks. Yeah, here in this figure I can show where the crack is. Yeah, it's loaded by a mechanical load, and the initial polarization was in this direction, and after loading you see, or perhaps you cannot see, these are little green arrows, and to make it a little bit easier for you, I have indicated here the domain walls, yeah, which separate the different domains with the different polarization here, yeah. And what is interesting in such a problem? Yeah, what are the driving forces acting at the crack tip, and what drives the crack? Yeah, at the end you are interested in not in the polarization field as it's given here, or in the stress field what you can compute here, yeah, or here, yeah. You are more interested in the driving force, in the configuration force, yeah. And as an example, we use this configuration here with here's the crack, here's the tip, yeah, of the crack, and this is the initial polarization. This is the, say, in this case, an electric loading, yeah, and what you then, yeah, here it's the problem again shown, and in this case you also have a loading by mechanical loads as two possible loading system. This is what you get, yeah, for instance, the stress distribution, strain distribution, and so on, yeah. The polarization field around the crack, and here are the configuration forces. And to see it in a little bit better, I have magnified this picture, and you see here are some spurial forces. This is, say, numerical dirt, yeah. But here, what you see here, these are really acting forces on the domain walls, yeah? And this really big force, this is the force acting, the driving force acting at the crack tip, yeah? And usually people take this to, yeah, compare it with, say, experimental, yeah, determined force which is necessary to drive really the crack. Yeah. Yeah, and here are some results. Yeah, plotted is the J integral. The J integral, this is a usual yeah, property or quantity used in fracture mechanics, yeah, it describes the driving force on a crack tip. And in this case, this is nothing else than a configurational force, yeah. J integral and configurational force at the crack tip are exactly the same, yeah. And here is the loading, the mechanical loading, yeah. And here are three different electrical loadings. Yeah? Plus means in the direction of the initial polarization, minus means in the opposite direction of the initial polarization, and zero, of course, nothing. Yeah? This is only electric than mechanical loading. Yeah? Okay. What you see here, if you have an electrical loading in the direction of the initial polarization, this curve lies below the others, yeah? And for the negative electric loading, this is the highest, yeah? Independent on the mechanical loading. And and here more or less the same, this is a crack opening, yeah? Versus the mechanical loading for different electrical loading, and the conclusion you can draw from this figure here is that positive electric field, yeah, inhibits crack initiation, because you need a much higher, say mechanical loading to initiate the crack, yeah, crack growth, yeah. And negative electric field promotes crack initiation. Yeah, and this is in agreement with experimental results. But I have to mention that the experimental results are not as clear as we would like to have it. Yeah, because there are other experimental results which say exactly the opposite. Yeah, but with this, it's an agreement, yeah. Now, one big issue is the boundary conditions you use for your computation, yeah, at the crack phase, and there are more or less 4 different boundary conditions on the market, yeah. Yeah. Permeable boundary condition, electrical permeable boundary condition, impermeable boundary conditions, or semi-permeable, so that you have some permeability across the crack faces, yeah. But then you have to know an additional constant here, yeah, and so-called energy consistent boundary conditions, which are in, say, from the theoretical point of view, the best, yeah, boundary condition you can have, yeah. And simulation can be done for all these boundary conditions, of course, but then you also need, again, material properties, yeah, and here you see for, say, the driving force versus electrical loading for different boundary condition, permeable, impermeable, semi-permeable, energy consistent, where, say, the parameter kappa, which was on the foregoing slide, was taken for water. This means an environment where the humidity is very high, yeah, yeah, which really can appear, yeah, yeah, and what perhaps one can see is that say in the positive electric loading regime, these energy consistent boundary conditions, they lead to the lowest driving force, yeah, and the permeable boundary condition to the highest driving force. Okay. the foregoing results were simulations with the material parameters we got, say, a couple of years ago, 5 years, perhaps 6 years, yeah. And now, just a few weeks ago, we got new material constants, which were not taken from macroscopic experiments, but from MD simulations and say microscopic experiments at single crystals. Yeah, and so we repeated our calculations, and then the result was such that there were big differences between, say, the old calculation and the new calculation, and which one is the correct one. Yeah, of course, because this material constant stem from MD simulation and micromechanical experiments, yeah, we now say, okay, this really can be used for simulations, say, in the nanoscale, yeah, and and what we now saw was that the results really depend on say the geometry of the structure. So you have really a scaling problem here. Yeah. Here is a driving force again. It's another notation here, and here you see the geometry parameter A. Yeah, and you see that the driving force now depends strongly on A. Yeah, the size. You have a size problem here. Yeah, this here is not a mistake. Yeah, this curve here shows that the microstructure at the crack tip changes here. The one system of domain walls is no longer stable and it changes to another, polarization pattern. Yeah, and this gives rise then to this jump, in this curve. Yeah. Okay. These results, as I mentioned, they are now 2 weeks old. Yeah, yeah. Okay, there's a lot of questions still open here, and the influence of the 2D and 3D simulation, of course, the boundary conditions. It's not always clear what boundary conditions you shall take. Yeah. Then, if you model a real structure where you have a polycrystal, yeah, then it's not always clear what the condition at the grain boundaries are. Yeah, and the initial conditions, yeah, the virgin state of the material, yeah, and so on. So there is a lot of questions still, and a lot to do still. Okay, I now will stop with the problem of piezoelectric materials, and you have to stop me or give me an advice on too long. This is a short part of my talk only. Dielectric elastomer actuators. This came to us from people from electrical engineering because they make a lot of experiments and use it as actuators. Want to, they had a problem with such actuators. This is very soft polymer. Yeah. Soft polymer with electrodes, yeah, and usually in a layered structure, not only one like here, more layered, electrodes and material in elastomer in between. Okay, a piezoelectric actuator, here the coupling comes through the constitutive laws, yeah, and you have only small displacement. This means it's very simple. You can apply small strength theory, and you can get large actuation forces, yeah, and in a soft actuator, elastomer actuator, the coupling between the mechanical and the electrical, fields comes through the Maxwell stresses, yeah, only, yeah, and electrostatic voltage forces. You can get large displacements and only small actuation forces. But for certain problems, this is exactly that what you want. Okay, again, simulation starts with modeling and basic equations. Again, the balance law here, the Maxwell stress is introduced directly, and then constitutive relation, kinematic relation, electric potential as before, yeah. And in the constitutive relations, we used for the mechanical part Neo-Hooke law, yeah. With this Neo-Hooke law, you can simulate many different elastomers, rubber or other materials, yeah. It's not a problem, but of course you have large strains, and this means the problem automatically becomes nonlinear, yeah. Okay, we do not only simulation with finite elements or finite difference method. We have also a lot of methods, but we don't go in the field of MD simulation and see deeper in the atomic structure. We have colleagues who do this for us, yeah. But we also like sometimes to do some analytics if it's possible. And this is one single case where analytics is possible, yeah. Take such an actuator, yeah. This is the electroactive material. These are the red and the blue are the electrodes, and you apply an electric field and electric potential between these electrodes, and you also can apply mechanical loads here, F1, F2, and so on. And you have an initial configuration given by L1 and L2. There's no mechanical or electrical load, and then on account of this load you get stretches. The stretches are given by these lambdas here. Here the initial dimension, here the deformed dimension of the system. What you then need are constitutive relations. Usually it's assumed that such a material is incompressible, yeah, and you have a mechanical stress and the Maxwell stress, yeah, and then the constitutive law, you assume that it's given by a potential phi here, yeah, and the potential phi can be very different, yeah. You can choose, yeah, and there are many different potentials to describe. such a material on the market. Yeah, and the rest is very simple. Yeah, it's you can give it to your students. Yeah, and equilibrium equation and some kinematics. Yeah, and what you get then at the end, after some analytics, you get say an equilibrium condition or configuration given by these, say, three equations. It makes no sense to introduce them one into another, given by these three equations. And then what the big issue here is, what can you say about the stability of the system? Yeah, because in electrical engineering, they always had a problem if they apply an electric load, for instance, or a mechanical load, they got electric breakthrough, or say really an instability. Yeah, and so we got an say condition for say stability, and it's given here, and what you see here is say the necessary electric field to get instability. Here the lambdas appear, and you see this is for phi was the potential, what describes in some sort the behavior of the material, and this is a very general equation which is valid for say all possible materials, or say if they have a potential, and and here I only want to discuss very shortly the result for the Neo-Hooke model. If you say take the potential for the Neo-Hooke model, then you get this for your say instability, or and what you see here is say a plot describing the electrical load, versus the stretch of the material, lambda. We start from this point here, from 1. This is the undeformed configuration, and then the stretch decreases, the lambda 3. This is the stretch in the thickness direction, and this is equilibrium, saying nothing about the stability, of course, and this is the curve describing, say, the stability or instability, and where these two curves touch each other or cross each other. This is the point where, say, if you load your system, you reach this point, then comes unstable. And this you also can do for other material laws, not only Neo-Hooke material and so on, and this you of course can also do with numerics, for instance with the finite element method, for then you are not restricted to say the geometry and the boundary conditions. But what you see is a perfect agreement between analytics and numerics in this case, and what you can do with simulation, you can optimize your composite, and you can also compute configurational forces if necessary. You also, and this we have done, simulations of the dynamic response. Okay, here only one slide of results. Here the only comparison between say numerics and analytics, and it matches perfectly. So numerics is good. Now, take for instance an actuator, a homogeneous actuator, yeah, the polymer between two electrodes, yeah, and yeah, and what you see, for instance, the compression versus the electric field here, yeah, and some people say, okay, this is not really satisfying, yeah, so for such a homogeneous actuator, we would like to have, say, a stronger effect of the electric field on the compression. And what you can do is you can put into the material piezoelectric material, yeah? Then you have a composite, yeah? And with this you change the overall electric material constants, yeah? And here we have done it only for one particle, barium titanate particle, where we have the electric constants, and put it into the polymer, and what you see, if this is a red curve, then yeah, you get a much better, or say in this regime, you get a better, say, compression or a stronger effect. And then what we now do, and one student is working on that, this particle, of course, is not the best choice of geometry. There are better choices. You have to think about the size of the particles compared with the thickness of the layer here, and the geometry of the particle. And incline, for instance, of elliptical or ellipsoid particles are much better, yeah? Then you get this much stronger effect here. Yeah. 5 minutes? Oh, I've still 2 parts. Okay, no, it's okay. Yeah, let me, in short, go into the field of ferroelectrets, yeah? What are ferroelectrets, or so-called piezoelectrets? These are electrically charged micropolar porous foams. Again, very soft material, yeah? Polymers with cellular voids, yeah? Open or closed porous polymers, yeah? They show the hysteresis in the polarization as in ferroelectrics, but what the difference is, they are soft, yeah, and they have a giant longitudinal piezoelectric constant up to, yeah, very high, yeah. Very low density, very low production costs, yeah, and the applications are in, for instance, in actuator technology, sensor technology, pressure sensors, for instance, yeah, acoustical devices like microphones and loudspeakers and so on. And these are only some applications, yeah, where these materials are used, yeah, and you can buy it directly. There is a company in Finland, yeah, who produce such, say, thin foils or sheets, yeah, and this is, a slide, yeah, as usual, which show that how you can use such materials for energy harvesting or sensors. So, what is the working principle of such materials? Yeah, in some sort you can say it's a composite. Yeah, this is a micrograph of such a material. Yeah, you see here you have electrodes. Here is the foam, or the material with many voids. Yeah, and if you apply a sufficient high electric field, then in the voids electric breakdown takes place. Yeah, and on account of the acting field, the charges are separated and transported to, say, the interface between, say, the gas and the, let's say, solid material. Yeah, and these and this is, and then at these interfaces the charges are really fixed. Yeah, they are trapped. Yeah, and these charges of course form then engineered dipoles. Yeah, and this leads to piezoelectricity. This is a very nice procedure, and what you see here, for instance, if you apply this electric potential in say two directions, up and down, you see what you can measure is the surface charge, but you see a hysteresis effect. Here for these micrometers is in this case the thickness of the sheet. And what is of interest, how to determine the piezoelectricity of the material, and is it possible to derive a complete material model, and this is possible, and it works very well. And I show only, if you allow me, how it works. You again model the solid material as with continuum mechanics, and also the material inside with continuum mechanics, but with other properties. And then you have, say, at least two parts of the system. Say, usual continuum mechanics, nonlinear, of course, all we described with the Neo-Hooke law, and the special interface here, This you have to take into account, and the interface behavior is also relatively easy to describe, and the Gauss law must be fulfilled across the interface, and this is given here. And if you have breakdown inside the voids, then the Gauss law is written in this way here, and only in short, what you then can do, look, you load the material, and have your first breakdown. This is given by this line here. You load it. There is not yet any charge at the interface. And here now you have breakdown, and if you increase then the external load, your P, this is the charge distribution at the interface, increases, and it decreases linearly. This is clear also from experiments, yeah. And then if you unload the material, yeah, then there is no longer breakdown, but the P remains constant, yeah. If you go to the other direction with your loading, you here touch this red curve, yeah, and breakdown takes again place, yeah. And if you look at this system, this looks exactly like a one-dimensional material where you have kinematic plasticity, yeah. And we can take all the use the tools from plasticity with kinematic hardening, yeah, to describe such a material, yeah. And I don't, yeah, here are some simulations, yeah, and what I only want to show is, say, comparison with between numerics and the experiments for one system, yeah, and here again, say the D33 component. This is the piezoelectric coefficient. What is really important, yeah. Okay. With this, I will stop and not go into nanomechanics. Thank you very much for your attention.
Have some time for a couple questions.
I have some curiosity. The first part you mentioned that one type of boundary condition in simulates humidity. How is that done? How humidity is incorporated into the properties of the material?
Oh. Ah, sorry. This is relatively easy. Here you see for the semi-permeable system and for the energy consistent system, you need a constant here, yeah, the susceptibility of the material, yeah, and the susceptibility in the gap between the upper and the lower crack face, yeah, this is air, yeah, dry air or humid air.
So
yeah.
it goes into the electric properties of the material,
yes,
not on
exactly.
the mechanical.
Yeah.
Just like changing the dielectric constant
Yeah, of course.
of the
Yeah.
void.
Yeah.
Any further questions? If not, let's thank Dietmar once more.